We live on the cutting edge of physics, materials science, engineering, and nanotechnology. Because at Lockheed Martin, we're engineering a better tomorrow.
A couple things before I begin. First off, I'm not Mr. Freeze, okay? My real name is Jerry Zimmerman. I'm a physicist at Fermilab. Now, Fermilab's a national lab run by the Department of Energy. We do a particular type of science called high-energy physics. We're in Batavia, Illinois, by the way. As I said, I'm a physicist there. And if you've ever seen The Big Bang Theory, okay, I am more the Leonard Hofstadter as compared to the Sheldon Cooper type physicist, okay? Well, except for I don't have a really hot girlfriend, so that's kind of a... But the area of science that I work in particular is called cryogenics. Now, cryogenics is not the science of crying. So there'll be no crying during this demonstration, but it is the science of the extreme cold, thus my nickname, Mr. Freeze. And before I start horsing around, I always like to give you a chance to see what I'm working with. We sometimes refer to this stuff as liquid air, but technically this is only a portion of the air. This is liquid nitrogen. That's it. It's just a clear liquid. In fact, if you didn't know better, you could actually very easily mistake that stuff for water. Now, there's a few things that we notice right off the bat that do seem a little different. First of all, what's this stuff coming off here? Seems hot. What's this stuff? It's fog. It's water vapor. Just like you see your breath in winter, same effect. Only this is caused by the fact that the liquid in the bag is so cold that it's condensing the water vapor out of the air around us. What's happening to the liquid in the bag? Bubbling. It's bubbling because it's boiling. It's boiling because everything's so hot that everything makes it boil. My glove is so hot to that liquid that my glove makes that liquid boil. Just like electric iron make water boil, my glove makes that liquid boil. Well, here's where you can help me out. If you want to know something, what do you have to do but ask a question? As I go through the show, I'm going to regularly go like this, and what I want you to do is ask me the question, how cold is it? So let's give that a try.
How cold is it?
It's so cold, it makes a snowman shiver. It's so cold, it turns Smurfs blue. It's so cold, it freezes time. Well, okay, that's what happened to my watch when I dropped it in there, but that's another problem. But what you really need to know the temperature of something is a thermometer, and I have a thermometer about 70 degrees, very nice. But actually pour this liquid on my thermometer so I can actually measure the temperature of the liquid. So I pour this liquid right on my thermometer like that, so I measure the temperature the liquid's really at. So liquid nitrogen is about 40 degrees. No, what happened? I didn't break my thermometer. The thermometer's working just fine. What it's actually measuring is minus 320 degrees. That's how cold this liquid is in these containers. And because it is so cold, it has a very powerful effect on lots of things. Now, one of the first things that we noticed was that the liquid was boiling. Now, when you boil water, what do you get but steam? This isn't water, this is nitrogen. So what am I going to get when I boil nitrogen? Nitrogen gas, or basically air. So I pour it in a little bag, seal the bag up. What will happen is that bag will fill with nitrogen gas caused by the liquid inside, expanding and inflating the bag. So you can see it makes lots of gas from just a little bit of liquid. Okay, I guess this bag wasn't big enough for this job, so I'm probably going to need a bigger bag. Actually, before I continue, I am going to need a little help with some math. Put your hands down. I'm going to give everybody a little mental math exercise. It's a very simple problem. Should be able to figure this out real easily. Now, I need to know how many seconds are, okay, seconds in a year. No, it's really easy. It's 12. Yeah, January 2nd, February 2nd, March 2nd, April 2nd. Oh, you thought I meant those other seconds. Oh, no. I thought it was a leap year and had a second for no good reason. And so I have a bigger bag here. Now, one of the things I could be doing as I do this demonstration, a little scientific investigation, that investigation is what you call the expansion ratio, or basically how much gas you get from a given amount of liquid. If I start with, say, 1 cup of liquid, how many cups of gas you get? Well, the way to find out, of course, is you take, let me open up my bag here, you take 1 cup of liquid, you put it in your bag, you seal your bag up, and you'll see how many cups of gas you get for each 1 cup of liquid. Now, this is a good-sized bag, lots of cups of gas. Kind of use the table here as a little bit of a hot plate warming it up for me here. Let's see. There we go. So now the question is, is this bag going to be big enough to hold 1 cup of liquid converted to gas? So what do you think? Yes? No? No. So tell me, what do you do when you have a little scientific setback? Do you give up? Do you quit? No! You buy a bigger bag. So I have a bigger bag here, and I can repeat my experiment. Start with 1 cup of liquid again into the bag. Now, the good thing about this bag is that I know this bag's, in fact, a 45-gallon trash bag. This bag here holds 45 gallons. But wait a second, I don't need to know how many gallons of gas I get. I need to know how many cups, because I'm trying to make a ratio of cups to cups. So I guess I need to know how many cups are in 45 gallons. Well, I guess first I need to know how many cups are in 1 gallon. So how many cups are in a gallon? 16 cups per gallon. 45 gallons in the bag. 16 times 45, okay, that's a little trickier. So is this bag going to be big enough to hold 1 cup of liquid converted to gas? 16 times 45, going once, you better hurry up. 16 times 45, going twice. And the question, is this bag big enough to hold 1 cup of liquid converted to gas? And the answer is yes. In fact, this bag is just big enough to hold 1 cup of liquid. Or actual numbers, for each 1 cup of liquid nitrogen, I get 700 cups of gas. By the way, 16 times 45 is 720, so this bag is just, why doesn't that bag float? See, it's not helium that's lighter than air, it's nitrogen, which is air. So it's like a big beach ball, not like a helium balloon. Now that's fine, but the truth is that's not very convenient. It'd be much better if I, actually had a container I could hold it in. Now, because I am kind of the clumsy sort here, I always make sure that I put a cork on that so I don't spill any of it. So, oh! Oh, that's what happens. Okay, now I understand, okay. Actually, by the way, this is kind of a neat way to demonstrate another principle of science. Is that if I kind of turn things around a little bit and do it this way. So, what principle of science was I trying to demonstrate there? Rocket propulsion. The reason why the bottle flies away, because it is just like a rocket. But the truth is, that's still really not what we do. What we'd really do is this. What happened in this case? The bottle blows up. Yeah, in fact, I know somebody at Fermilab, when they did this demonstration and the bottle blew up, it broke his nose. Good seats in front, right? But wait a second, why would somebody knowing the bottle's going to blow up be standing here holding it? See, one of the things about working in science is understanding how to handle things safely. So how do you prevent the bottle from blowing up? You poke a hole in the lid. By the way, bazinga. It's the only thing I learned from that show, by the way. So at the end of the show, I'll actually be detonating one of those bottles so you see how powerful it really is. So we've investigated the gas expanding. Now I'm going to investigate what happens when you introduce a gas into it. What's going to happen to a balloon? It's going to pop, it's going to freeze. What's a frozen balloon look like? Well, we'll find out, put it in here, see what happens. Oh, this is quite interesting, yeah. It's going to change color. Oh, no, wait a second, no. It's going to change shape. Okay, there seems to be a problem. No, that's not it, okay. Is that, nope, no. How about, no. How about that? No, that's not it, okay. Is that, nope, no. How about, no. Is that, no, that's not it, okay. Is this one? No, that's not it, okay. Is this, no, okay. How about, no. What color is that balloon I started with here? Wait a second. Yellow, there it is, okay. The air inside those balloons collapses that 700 times, shrinking down into air. Once they bring the balloons out, the air inside warms back up, re-expanding, re-inflating to the same shape and size before it started. That's the reason why those balloons are able to size. Sometimes they don't survive, what can I say? Actually, in sort of an odd timing thing, I recently got done working on an experiment at Fermilab, and this is the truth, okay? The name of that experiment is called the dark side. I was working for the dark side. It's hard to recruit people to work for the dark side, by the way. It's actually a cryogenic detector in Italy. If you decide to Google that, you need to Google dark side 50, otherwise you'll never find it in a million years. But when I was asked to join that experiment, I was told it's going to require some long hours, some weekends, and they said, okay, if I join your experiment, what do I get out of it? You know what they said? They said they'd give me a lightsaber. I was expecting something other than a very, very light saber. By the way, I don't think these things are that dangerous. I don't know what the big deal in the movie was. Well, they can't hurt anybody, right? By the way, this is good for something. It's very good at making cold cuts. You do know what this is, of course. It's a special type of puppy dog. No? It's you're not watching. It's a chili dog. Chili, never mind. Yeah. I was going to use this balloon. Oh, it doesn't fit. Oh, wait a second. What if I help it along? As the air inside that balloon cools down, it collapses. Remember from the movie right by now, she's saying, Dorothy, you wicked little girl. As the air inside that balloon cools down, it collapses in my container. What about a more rigid container? This is a, where'd it go? Around here or something. This is a regular bottle, and we'll put a regular cap on it. You've seen this in the Pepsi commercials. How about an even more rigid container? This is, stay. This is an empty can. I sealed the top with tape, so now basically it's just an aluminum balloon. Now, one of the things that's interesting about this, what happened to the balloon when I brought it back out? It reinflated, came back exact same shape and size. Help the plastic bottle along my hands here, warming it up. Plastic bottle comes back. Aluminum can does not. There's a reason for that. Some materials are permanently affected by the cold temperature. In this case, aluminum actually becomes a stronger metal. It's actually called cryo treatment. It's very standard in the machine industry nowadays to cryo treat different metals like aluminum to make them stronger for certain applications. So if you ever see on a product cryo treated, that's basically what they did, is they dipped it in liquid nitrogen. You'll notice when I'm working up here, it does kind of look like I'm reaching into the containers, and I can actually see where the liquid is inside containers. I have different things for different jobs. I have these blue gloves. These are special cryo handling gloves designed to handle extremely cold things. I have the tongs, very good for taking like balloons in and out of liquid nitrogen. But you'd think the hazard of this stuff is that you wouldn't want it to get on your skin. So you'd wear some type of protective gear to protect your skin from contact. Now this black glove is perfect. This is a special glove. It's kind of expensive because it has been guaranteed tested liquid tight. So no liquid can get through this glove onto my hand. So this glove's perfect for me to, reach in and grab some. Is this a bad idea? I mean, what's going to happen? Like fingers going to bust off? No, I didn't actually lose any fingers in this demonstration. But this glove isn't very good at working in cryogenics because this glove itself changes into something that's, in fact, much more like glass. In fact, why do you think I'm wearing this white glove? Because of the cold temperatures? No. Because if I did that with glass, what would happen to my hand? I'd cut my hand. Do you know how hard it is to explain to people how you cut your hand on a rubber glove? Show me a bit. Sorry, it was really sharp before. But what would really happen if I put my hand in there? If I put my hand in there for a few seconds, I'd get on my hand what is called a cryo burn. Very similar to a fire burn, same body physiology going on. In fact, a few minutes later, all the skin would peel off my hand because it burned the skin off the hand, same as the second on fire. Actually, my hand in there for about 5 minutes, it would freeze solid. Now, as compared to those TV shows and movie scenes, you do not shatter like glass. That's not the way the body is. The bones stay about as strong as they are now. But having said that, what in the world would I be thinking of to hold in my hand? Why can I not put my hand in the container there, but I can hold in my hand here? And the reason I can do that is actually called the Leidenfrost effect. And the Leidenfrost effect says that anytime you put something that's much warmer than the boiling temperature of the liquid involved, it actually doesn't come in contact. In this case, this nitrogen actually isn't touching my skin. My skin isn't getting wet because it's not touching me. The real hazard of liquid nitrogen is not your skin. It's in something that can actually absorb a liquid. This cloth is wet with nitrogen. If that cloth against your skin, you transfer the cold temperature, giving you a burn. You ever go to a doctor and get a wart burned off? What they use is a cotton swab or a Q-tip to transfer that cold temperature, kill whatever they're trying to get rid of. Now, I quite often get asked, by the way, a little background, Fermilab does allow me a couple of days of my regular work here to go to area schools in the Chicagoland area to do this demonstration, to promote science in the classroom. It's provided free of charge by Fermilab. And I usually get asked whenever I do one of those demonstrations, can I do that? And if you notice, okay, when I do this, I'm very careful not to toss it where I'd get on myself or toss it where I'd get on somebody else. So the only way I can actually teach somebody how to handle liquid nitrogen is what? Is if everybody in the area is naked. So if you weren't wearing any clothing right now, this would be a perfectly safe demonstration, right? Oh, wait a second. There's something else on your body absorbs liquid, isn't there? Hair, yeah. See what happened to me? No, there's nothing to do with working in nitrogen. This is pretty neat stuff. This here is a 4-liter dewar, 4LD. Now, 4 liters is about, how much in US terms? It's about a gallon of liquid nitrogen. So how much do you think a gallon of liquid nitrogen costs? Is it like, $5 a gallon? $10 a gallon? Try $1 a gallon. In fact, in really large quantities, like we get at Fermilab, we actually get liquid nitrogen for 25 cents a gallon delivered. So why is it so cheap? First of all, where do we get it from? The air. All the nitrogen I'm throwing around here is going in the air. You're breathing it all in. You'd be so kind of to breathe it all back out again. It's just a recyclable. By the way, I am responsible for accounting all the nitrogen that I put out here, so I'm going to have to account for all the nitrogen you guys are breathing in, okay? So make sure you breathe it back out again before you leave. Secondly, what do we really need out of the air? Oxygen. Liquid oxygen is much more valuable, much more commoditized. Nitrogen kind of a byproduct. Now, it's a good thing it is so cheap. We do use a lot of it there from that. Ever seen those big trucks go down the highway? Each one of those trucks holds 7,000 gallons. We use 3 of those trucks every day. But you know if companies use more than we do. In fact, you've eaten stuff frozen. Yeah, Ronald McDonald used liquid nitrogen to freeze that hamburger you ate last week. You ever wonder why it looks the way it does? I know. It's not all bad. Okay, first off, it's 25 cents a gallon. You can freeze a hamburger for 25 cents. Secondly, it's just nitrogen. You can dump a truckload of stuff directly on the food, and it will not affect the quality or safety of the food. And the third reason the McDonald's Corporation does it, I can demonstrate this way. I'm going to put some water in this bag, and now I'm going to add some liquid nitrogen. Now, this kind of machine demonstration in itself. I have in this bag 2 liquids. One liquid is boiling, while one liquid is freezing. One liquid is going from a liquid to a gas at the exact same time as another. So which one is boiling? Nitrogen. Which one's freezing? What am I making? By the way, it's so cold it makes ice scream. Oh, no, wait a second, that came out wrong. Screaming ice. We just turn around the other way. That works out okay. By the way, isn't that what you get when you pinch Olaf is screaming ice? Okay. Okay, I guess it's screaming snow. I don't know. Now, this ice I'm making here is regular standard water ice. A very odd shape because of the way it's formed. But it also has the property, if you get all this water piece, that this ice is so cold, there we go, that it freezes to your skin. It's so far below 32 that it freezes to me before I melt it. Same idea as sticking your tongue to a flagpole in midwinter. Don't do that. It really works, kids. If you want proof, we'll show you the movie again. And again, and again, and again. So what would happen if I tried to eat that ice? Freeze to my tongue. It'd be pretty painful, yeah. So what in the world would I be thinking of with a marshmallow? I obviously don't have a campfire up here, so I have to use the next best thing, which is, of course, liquid nitrogen. So now the question is, what do you do with a very well frozen marshmallow? Now, some people have suggested I make s'mores. The problem is s'mores are supposed to be mushy, and this is no longer mushy. It's now crunchy. So now the question is, what do you do with crunchy marshmallows? It's not make Lucky Charms. I'm really not sure what those things are, but I'm pretty sure they're not marshmallows. Actually, if you don't mind, I didn't have a chance to have lunch, so if you don't mind, I'll just kind of have this as a snack. I'm sorry. I should not be smoking in front of you kids. Well, that was smoking, that was fogging. It's okay to fog. But wait a second. Why wasn't I able to marshmallow? One of the things about marshmallows that most people don't realize is marshmallows, in fact, are extremely good insulators. What insulators do is they don't transfer temperature well. That's why you insulate your house. Well, marshmallows are almost as good as the insulation you have in your house. Don't go home and insulate everybody all kind of trouble hands. But a marshmallow is such a good insulator, it will not transfer the cold temperature of the ignition to me well. So even though it's just as cold as the ice, I take it out and eat it and it will not give me a burn. Ice isn't near as good. Will transfer the cold temperature fast enough, give me a burn, be very painful. Now, I quite often get asked, why in the world do we use so much liquid nitrogen in their Fermi? And I demonstrate that with this. I have here an electromagnetic coil, and there's a property called Lenz's law that anytime you put an electrical conductor into a changing magnetic field, it produces a current in that conductor, and that current produces a magnetic field that's opposite. So in this case, when I activate the coil, now that's good. But we at Fermilab don't want our electrical conductors just to be good. We want them to be really good. So how can we make this a better electrical conductor? By doing this. By cryogenically freezing it, it will become a better electrical conductor. When it becomes good, it'll make a higher current. Oh, by the way, almost forgot. It's so cold, it gives goosebumps to a penguin. It gives a slushy brain freeze. It's so cold, it gives you brain freeze just thinking about it. Oh, okay. So now that my ring has been cooled down to cryogenic temperatures, it now is a better conductor. And when you put a better conductor into the same magnetic field as before, you get good catch. Almost a good catch. But the reason why it goes higher is because it is a better electrical conductor there, so it produces a higher current and goes much higher in the air. Now, okay, next thing, going to do a little experiment, going to do a little background demonstration first. I have here a tennis ball, actually the stage might be better, the racquetball, tennis ball. You can actually hear something quite unique in this setting if you try to listen very carefully. Racquetball, not that much. Tennis ball, kind of popping sound you heard was actually thunder. Thunder, how could that be thunder? What thunder is a sonic boom caused by air expanding faster at speed of sound. In case of a lightning bolt, it's the heat of the lightning bolt causes the air to expand so fast. In this case, the cloth coming to the tennis ball caused the nitrogen to expand so fast as to exceed the speed of sound expansion. Now, I do this as kind of a background demonstration, but it's kind of interesting by itself. You ever wonder why certain sports don't catch on really big in certain parts of the world? This is a good example. Racquetball, Alaska, not a good idea. I don't recommend it. Hit by that, you're probably going to be sorry. The Alaska Open, not one of those big tour events, and the old tennis are out there anytime soon. Hit by that tennis ball. Actually, in Alaska, they do not call it tennis. Do you know what they call it? Dodgeball. Hit by that, you're out. You're going to a doctor, hospital, something like that. But now I do that as kind of a background demonstration. Whenever you're doing a science experiment, what you're actually trying to do is answer a question. So in our case, our question is, what do you think is going to happen to this ball? Now, before you do your experiment, you come up with your hypothesis, your educated guess. In our case, we could look at similar examples. We did a balloon. What happened to the balloon? Collapsed and came back. We did a racquetball, tennis ball. What happened to them? They got hard. So what do you think is going to happen to this? Is it going to collapse like the balloon or get hard like racquetball? We'll see. We'll put it in here and see what happens. Oh, it didn't collapse. Got hard like racquetball, tennis ball. Okay. But what happened to the air inside that ball? Did it still collapse? Yes, it did. It had to, because it got cold. It had to collapse. So now I have a hard brittle exterior with a collapsed gas or vacuum inside. What does that make this like? No, I'm not voting. I'm pointing to a light bulb. Tell me, what happens to light bulbs when you hit them? Whoops. They explode. Yep. The reason why that ball explodes that way, because it is just like a light bulb. When it hits, it implodes into 1,000 little pieces, just like a light bulb would explode. Okay, next one. This one. This one, oops. This one, I forgot. Hang on a second. Flowers. This one, I almost forgot, is for you ladies. No, I'm not giving you flowers. But you ladies should know the connection between flowers and cryogenics. And it's something about flowers we like. They smell nice. If you want to smell a freezing flower, you take a flower base and rub it on your cheek, give you rosy red cheeks. Well, if you start with a red rose, right? But wait a second. Where do you get that pretty flowery smell? Perfume. Well, how do you get the pretty flowery smell into the perfume? They do it this way. By cryogenically freezing the flower. All the fragrance gets locked in the petals. Then the flowers can be taken out. The petals can be crushed. The fragrance processed into perfume. Most flower-based perfumes use cryogenics to process the flavor out of the fragrance out of the petals. Oh, by the way, it's as cold as the heart of a guy that would do that to a flower. Oh, that's me. I'm sorry. A little too much information there. Okay. I think you're ready for this. Actually, if you could just wait 1 second. I'm a little thirsty. If you don't mind, I'm going to have a drink of my pop here. You know what? My pop's warm. I don't like warm pop. Oh, wait a second. I got this, see. I have this little thermos. You know what I can do? I can take and put some of my liquid nitrogen stuff right in my little thermos. Oops. Right in my little thermos like that. Then I just take my pop, put the cap on. In just a couple of seconds, I'll have a nice, this will be great because it's only going to take a couple seconds for that to get nice and cold. So oh. Well, the good news, my pop's cold. Oh, but now it's flat. I don't like flat pop either. By the way, if you're wondering what happened, at the point the pop reaches its freezing point, all the carbonation comes out of the liquid, causing it to come squirting out of the bottle. Hey, wait a second. Is that the reason why they call them fountain drinks? I've never seen a fountain drink. Oh, never mind. By the way, kids, you want a fun experiment to do at home. On a very cold winter morning, take a bottle of pop, poke a hole in it, sit out in your driveway. In about 10 minutes, it'll do exactly that. Do not do that in your mom and dad's freezer. I'm not responsible for the mess made at home. Outside on a cold winter morning, okay? Okay. So let me explain what's going to happen here and what happened to that poor guy in Fermi Lab I know. Basically what he did is he took one of these little plastic bottles, he put some in there nitrogen, put the cap on it, threw it in a trash can, stepped back and waited for it to go off. And he waited, and he said, I must have done something wrong. So I looked inside the trash can, see what's going on. That's when the bottle went off, hit him in the face, broke his nose. What he did not realize is A, how long it takes when it goes off, and B, how powerful it is. Without any help, this bottle takes 3 minutes to develop an artillery explode. When it goes off, it has over 250 psi pressure. That's what this bottle is designed to withstand. When I was trying to figure out how to do this demonstration for schools, I can't wait 3 minutes to see if the bottle's going to go off. Had to come with a solution to this 3-minute problem. The solution is pretty straightforward, and actually I showed you. What can I add to this bottle to make the nitrogen boil faster? Water. As you saw in the Ziploc bag, this now makes the nitrogen boil so much faster that now this bottle will take about 15 seconds. Now 15 is enough time to put it in the can and step back, but it isn't so long to wonder if it's actually going to go off. By the way, I can prove to you that it's the mixing of the nitrogen in the water by doing this. If I take and add some nitrogen to this bottle, not that much going on. But if I do this, whoops, it takes off. Guys, thank you. The reason why that bottle took off that way is because it is the water, nitrogen boils so fast that it shoots a jet of water that shoots the bottle away. So, I need to be absolutely sure about just one thing, and that is, are you ready? Now that 15 seconds actually does not start until after I put the cap on the bottle, because that's when pressure actually starts building. So until that time, there is no hurry. There's no hurry at all right now. It's not until I do this that now I have 15 seconds, and I cannot stop it. Snowing in here? Oh. This is all that's left of the poor bottle that gave its life for this demonstration. As you see, it don't survive it all too well. Secondly, it always amazes me, no matter how many times I do that, I'm always able to hit that confetti bird that's flying overhead, just knock him right out of the sky every single time. Now, normally, that would be the only loud explosion I do during a show, but I've been asked to do this show in venues that do not allow me to shoot a cannon off. I do a show in Wheaton, Illinois every year, and every year I do the show, I actually blow a hole in their ceiling. It's even more amazing, they actually invite me back every year. So I tried to come up with a solution to this problem. The solution is pretty straightforward. Instead of using a cannon, I use a cardboard box. Now, the advantage of the cardboard box is it doesn't shoot up, it explodes out. The other advantage of the cardboard box is because it's made of absorbent material, I can actually use a little bit bigger bottle and end up with the same sound level explosion I would with a smaller bottle in the cannon. But in certain situations, I'm not limited to the little bit bigger bottle. I can actually use the little bit bigger bottle. But wait a second. In certain situations, I'm not even limited to the little bit bigger bottle. I can actually use the big bottle. So I will leave it up to you. How many of you would like to hear the little bit bigger bottle? How many of you would like to hear the little bit bigger bottle? How many of you would like to hear the big bottle? Now, it's pretty straightforward and somewhat surprising. Pretty much everything remains the same. I still add the water to this bottle to make the nitrogen boil faster. I still add the liquid nitrogen, and in about 15 seconds it goes off. The difference between, of course, instead of shooting a cannon off, it's going to blow that cardboard box to pieces. So, I need to be absolutely sure about just one thing, and that is, are you ready? Oops, where's my, there it is. Oh, there it is. Okay. Okay, guys, sit down, please. Sit down. This, again, is all that's left of this poor bottle that gave its life for this demonstration. As you see, it didn't survive it any better than the last one. So, okay, I have one more demonstration to do. And the reason I do this particular demonstration is that I cannot legally transport the liquid nitrogen in these open containers. I have to do something to get rid of this nitrogen. So I came up with a solution to this problem. It's kind of a neat little demonstration by itself. Could I, here, let me put this over here. Could I have a volunteer from the audience? Let's see. Would you like to? This is Karina. She's going to help me out here. I have here a bucket of water and some soap solution. And Karina, if you could put a little of this soap solution in the bucket of water, so you go ahead, you do that. I'm going to take the liquid nitrogen I have left up here. Go ahead. This here. And I'll take this here and pour it in the bucket like this here. Now, for Karina, having done such a wonderful job there, I'm going to reorder with one of these very...
You told me, I asked you, you said
I was going to reorder with one of these very nice flowers for doing such a wonderful job. But I think I said a little soap. Does that seem like a little soap to you? Does she still deserve the flower? I don't know. I mean, wait a second. The way to thaw my frozen heart. Thank you very much. Thank you. See, the idea behind this was pretty straightforward. By taking that soapy water and mixing it with the nitrogen I have left, you see some bubbles made. Well, obviously, it's very soapy water. It's kind of has to do this on the kind of 3 type thing. So a couple things before I continue. I do have a Facebook fan page, I have a website. There's some neat videos up there to check out slow motion of the box blowing up and all that. Fermilab has a booth at 5319. Come by. We'll be making some marshmallows for you to try, give you a chance to taste a little cryogenics there. It's fun to do. But now I need to check a couple things. The first thing I need to check is, are you ready? The second thing I need to check in this case is, am I ready? How come I heard lots of yes? Okay, I have to try that again. Are you ready? Am I ready? Yeah, okay, yeah. I forgot. You're kids. You don't know the word no. So, yes, we do. So, on the count of 3. 1, 2, 3. Oh boy. Okay. Well, I guess, guys, back up. Guys, sit down. I guess I'm gonna have to change my name to Mr. Bubbles here. Oh boy. I always like to be sure that whenever I do one of these demonstrations, that you kids get to leave this little demonstration with something. It's not a shower like I just got. What you're gonna get to leave this little demonstration with is a little science homework assignment. Okay. Actually, kids, I would almost be willing to bet you that you'd have a hard time not doing this homework assignment. See, your homework assignment has to do with where I work, Fermilab. Fermilab's claim to fame is that we have some of the world's most powerful particle accelerators. We actually have one particle accelerator that shoots the particles right through the Earth from Illinois to Minnesota. So, how many of you have a particle accelerator home? I have 5 in my house, so I imagine you have one. So now the question is, what in your house what do you think you have in your house that's a particle accelerator? Any ideas? I do not have 5 microwaves. I can actually walk to the kitchen and get my food. Second way, microwaves generate what? Electromagnetic waves, which travel at the speed of light, so you can't accelerate that. So, any other idea? Okay, I'll make it easy on you. You watch it every day. Your TV set, your cathode ray tube is an electron gun. It accelerates electrons up to bombard the screen. So your homework assignment, kids, is to do what we do there at Fermilab, and it's not watch TV, okay? Is to go home and operate your particle accelerator. You didn't handle that one, right? You haven't lost the remote, right? Well, I hope you enjoyed the show, and I hope you learned a little something along the way. So thank you very much.